welcome everybody as well for this week on zeros of graph polynomials. I became interested first in chromatic polynomials a long, long time ago. And it was our first speaker, Alan, who convinced me that maybe looking at the multivariate approach and complex roots of polynomials was powerful. So I'm really happy to have Alan as the first speaker who will speak about complex roots of graph polynomials.
Okay, thanks, Bill. So first I'd like to thank the organizers for inviting me. So what I'd like to do here is give an overview of some of the issues that arise in looking at complex roots of principally the chromatic and flow polynomials and more generally all special cases of the multivariate Tutte polynomial. So it's intended partly as an introduction to other talks that will come later, and then Bill will do the same thing in the next talk about real zeros. All of the polynomials that I want to discuss in this talk are special cases of what I call the multivariate Tutte polynomial. So I have a graph VE. I have one global variable Q, which you should think of as the number of colors, or it will represent in certain specializations the number of colors, but it's just an algebraic indeterminate, which I will then specialize to be a complex variable, and Bill and other people will specialize to be a real variable. And then for each edge E, there is an edge weight, which I call V sub E, and I'll collect all those edge weights into a vector V. So multivariate means that I put separate weights on each edge. I'll try to explain why I think that's useful, even if your ultimate goal is to study a univariate specialization. And then the multivariate Tutte polynomial is simply defined as this polynomial ZG of Q and V, sum over all subsets A of the edge set. You get a monomial product of the VEs for that edge set. So you write all of the monomials, and then each one gets a factor Q to the K of A, where K of A is the number of connected components in the spanning subgraph, that is the subgraph with vertex set V and edge set A. So this is the polynomial, this is the most general polynomial I want to study, and it's going to contain a lot of other things as special cases. If you specialize all the variables V to be equal, then you get a two-variable polynomial ZG of Q and V, which is essentially equivalent to the standard two-variable Tutte polynomial TG of X and Y, except that there's a change of variables between Q, V, and X and Y, which is designed to obscure the fact that Q and V play very different roles. Namely, Q is a global variable, whereas the V's can be promoted to separate variables on each edge. So I think it's useful to use the QV notation even if you are ultimately interested in the univariate case. But that's partly a matter of taste. But what I will try to show in this talk, and Bill will continue showing, as I said, is that even if you ultimately want to do a univariate specialization, it's very often useful to look at the multivariate one first, because there are many operations that you can do on a graph that are useful, like series and parallel constructions and so on, that will lead you out of the class of all VEs equal. Okay, so just very quickly, what are some of the interesting special cases of the multivariate Tutte polynomial? And I won't have time to prove all of these things. But I should say everything, if you weren't here last week, everything, or all of the preliminaries for that I'm going to be going over fast are in my British Combinatorial Conference 2005 review article, which you can find on the archive. So, okay, what are some interesting special cases? If Q is a positive integer, then this specializes to the partition function of the Q-state Potts model in statistical mechanics. The proof of this is a nice, very nice two-line calculation which is physicists call the Fortran-Castellane representation. Physicists call VE positive ferromagnetic because it means that adjacent sites like to be colored the same. They get extra weight if they're colored the same. VE between -1 and 0 is antiferromagnetic because adjacent sites like to be colored differently. And VE equals -1 is what physicists would call zero temperature. Antiferromagnetic, nearest neighbors must be colored differently. So in particular, VE equals -1 counts proper colorings, and therefore ZG of Q and -1 is the chromatic polynomial. And by the way, this gives one proof that the chromatic polynomial is the restriction to integers Q of a polynomial. Okay, another special case is the flow polynomial, which counts nowhere zero flows over taking values in an abelian group of order Q, and that turns out to be some uninteresting prefactors times ZG of Q and -Q. And of course, the flow polynomial and the chromatic polynomial are dual to each other, on planar graphs at least. And this is a special case of a more general duality for the multivariate Tutte polynomial. Again, if the graph is planar, so it has a planar dual, then ZG of Q in any edge weights V is, again, some prefactors that I won't write down because I don't remember anyway, times ZG star of Q, and I'll write it as Q over V vector where that's understood element-wise. That is to say, duality takes VE into Q over VE. So in particular, it takes -1 into -Q. Okay, what other preliminaries do I want to make? The multivariate Tutte polynomial satisfies a deletion contraction law, which I'll just write down quickly because I'm not going to use it in this talk. To my knowledge, it's not very useful for studying complex roots, but it's extremely useful for studying real roots, as Bill will show you. It's just ZG delete E plus VE ZG contract E, and that's very easy to see. Well, it's easy to see. So that's deletion contraction. More interesting is there are series and parallel laws. That is to say, if you have two edges in parallel, I should say, for all of this work, it's natural to consider graphs where loops and multiple edges are allowed, because even if you don't have them at the beginning, they might be created by the operations that you do, like contraction. If you have two edges in parallel, it's easy to see that that's equivalent to a single edge with weight V1 plus V2 plus V1 V2. We call this V effective. Or another way of saying it is 1 plus V effective equals 1 plus V1, 1 plus V2. So 1 plus V multiplies. That's the parallel law. The series law, V1, V2, turns out to be equivalent to a V effective, which is a little funny. It's V1, V2 over Q plus V1 plus V2. The series law, unlike the parallel law, is Q dependent. And you can write that if you want, do a little algebra. It's 1 plus Q over V effective equals 1 plus Q over V1, 1 plus Q over V2. So series says 1 plus Q over V multiplies. And notice those two are related by V goes to Q over V. That's because series and parallel are related by duality. Again, if at least with planar graphs, the dual of a series connection is a parallel connection. So I'm going very, very fast. To prove each of these things is a few lines of calculation. It's not a big deal. I'm just trying to get down some of the techniques that will be useful later. Finally, let me talk about q goes to 0 limits of the multivariate Tutte polynomial. So let's start with zg of q and v. And there are various ways you can take q goes to 0 limits. The most obvious one is take q goes to 0 with the v's fixed. Then you'll pick up the spanning subgraphs with the minimal number of connected components. Now, the minimal number of connected components is 1, assuming that the original graph is connected. And so once you pull out a factor of q, what you will get is the generating polynomial of connected spanning subgraphs, which I call Cg of v. So this is the multivariate generating polynomial of connected spanning subgraphs. So that's q goes to 0, v fixed. And this is, by the way, essentially equivalent to the reliability polynomial of the graph. If you consider this graph to be a communications network with unreliable edges, which function with probability p sub e and fail with probability 1 minus p sub e independently for each edge, and you ask, what is the probability that every node can communicate with every other node, the so-called all-terminal reliability, then what you want is you want the set of functioning edges to give you a connected spanning subgraph. So up to some simple change of variables, I think the v's are p over 1 minus p, or the other way around, I'm not sure which. Yeah, p over 1 minus p, then this is essentially the reliability polynomial. That will come up later. The other kind of q goes to 0 limit that you can do is you can take q goes to 0 with the v's scaled proportional to q. That is, q goes to 0 with w equals v over q fixed. And then you do a little calculation, and you'll get q to the cyclomatic number. The cyclomatic number is the number of linearly independent cycles in the graph. And of course, the minimum possible cyclomatic number is 0. There are no cycles in the graph. And therefore, in the limit, after you pull out the right factor of q, you will get the generating polynomial of spanning forests, the spanning subgraphs that have no cycles. Notice again, these two things are dual to each other. Connected spanning subgraphs are dual to spanning forests if the graphs are planar. And then finally, you can start from connected spanning subgraphs, and let's scale all the v's from v to lambda v, and then let lambda goes to 0. Then, and again, pull out the appropriate factor of lambda. This will pick up the connected spanning subgraphs with the minimal number of edges, and those, of course, are spanning trees. So you get the multivariate spanning tree polynomial. Or you could start with spanning forests and scale, let w go to lambda w, and let lambda go to infinity, and you'll pick up the spanning forests with the maximal number of edges, which are, again, spanning trees. So you have this scheme of double q goes to 0 limits in the multivariate Tutte polynomial, which shows you that the multivariate Tutte polynomial is very rich. It contains a very beautiful quantity, namely the multivariate spanning tree polynomial. By the way, note, the univariate spanning tree polynomial would not be very interesting. It would just be the number of spanning trees times v to the n minus 1. But the multivariate polynomial is very rich, as you'll see. And then there are these further generalizations in the q goes to 0 limits. I don't have really time to explain it in detail, but the spanning tree polynomial is intimately related with electric circuits. This goes back to Kirchhoff in 1847 and mathematically comes from the matrix tree theorem that says if you write the weighted Laplacian matrix for a graph, that's the matrix that will come up in electrical circuit theory, then after you kill a row and a column, the determinant of that matrix is nothing other than the spanning tree polynomial. And so the spanning tree polynomial is more or less equivalent to elementary electric circuit theory. And as I will show you in a second, interesting properties of the spanning tree polynomial have interpretations in terms of electric circuit theory. And a lot of interesting questions come from taking things that we know about electric circuit theory and therefore about the spanning tree polynomial and asking, can we find analogs for connected spanning subgraphs or spanning forests or maybe even for the general multivariate Tutte polynomial? And I'll show you some examples of that. And then finally, before I go any further, let me just mention the generalization of this, all of this, to matroids. If you don't know what a matroid is, don't worry. 5 years ago, I didn't know what they were either. But I'm now convinced that matroids are really the right setting for studying the multivariate Tutte polynomial. They're a combinatorial structure that generalizes graphs and also generalizes linear algebra in a certain sense, or projective geometry. So if you have, let me start with the graph quantity and define first make one trivial change of variable zg tilde. Let me pull out q to the minus number of vertices. So I'll get sum over subgraphs a q to the k of a minus the total number of vertices. So this is just a trivial rescaling. You now have a polynomial in the v's and in the variable 1 over q. And then you realize that this, in matroid terms, is minus the rank of the subset A in the cycle matroid of the graph. So you just say, OK, I will make the definition for any matroid M. I will define its multivariate Tutte polynomial Zm tilde to be sum q to the minus rank in M of the set A, and then the monomial. So the multivariate Tutte polynomial is very naturally defined for matroids. Duality looks nicer for matroids than for graphs. For graphs, you only have duality for planar graphs. For matroids, you have it for all matroids. And all of these identities generalize for matroids. So I think matroids are the right category for looking at the multivariate Tutte polynomial. Of course, some theorems may be true for some matroids and not for others. They may be true for graphic, but not for cographic, or for graphic and cographic, but not for something else. So if you get bored with graphs, if I don't give you enough open questions for graphs, go to matroids. And in particular, these q goes to 0 limit immediately generalize to matroids. In place of connected spanning subgraphs, we have the spanning sets in the matroid. In place of spanning forest, we have the independent sets in the matroid. And in place of spanning trees, we have the bases in the matroid. So, for example, the basis generating polynomial is a natural generalization of the spanning tree polynomial. OK, now, with all of these preliminaries, now let me start talking about complex zeros of these various polynomials. First of all, why on earth would a physicist care about complex zeros of these polynomials? The parameters for a physicist, well, the parameter q is usually an integer, positive integer. The parameter v is related to couplings or temperatures. Those are certainly real numbers. You don't go to your experimentalist friend and say, please measure for me the specific heat of iron at 273 plus 6i degrees Kelvin. Nevertheless, it turns out that complex zeros of these polynomials are of great interest to physicists. And let me just sketch very, very briefly why this is so. And then you can look in my review article for more information. And also, Robert Schock will talk about it more in his talk Thursday, I guess it is. So why do you care about complex zeros? It has to do with the notion of phase transitions. A phase transition is any situation where some observable parameter, the magnetization, the specific heat, whatever, something that you can measure, depends in a non-analytic way on some control parameter like temperature or externally applied magnetic field or whatever. And non-analytic means in the sense of analytic function theory. So it could mean discontinuous. It could mean continuous but not once differentiable. It could mean 17 times differentiable but not 18 times differentiable. And it could mean C infinity but not analytic, things like e to the minus 1 over x. And all of these types of phase transitions actually occur in physics. But the classic example is take a magnet, say iron, take a sample of iron at room temperature and apply an external magnetic field, little h, and measure the magnetization of the magnet, and you will get a curve that looks like this, which is discontinuous at zero magnetic field, because roughly speaking, these little atomic magnets like to point in the same direction as their neighbors. So they want to get either most of us going up or most of us going down, but they can't decide which. At zero external magnetic field, there's a symmetry between up and down. As soon as you turn on a non-zero magnetic field, you break the symmetry, you break the instability, and the little atomic magnets get together following the external field. So you get a discontinuity like this, and I ask, how can such a discontinuity occur in a polynomial like the one I wrote down and erased, or in any statistical mechanical model? And the answer is it can't. Any statistical mechanical system with finitely many degrees of freedom, everything in sight is analytic. It can't possibly, I mean, it's a polynomial. How better analytic than that can you get? You can't have phase transitions in a finite system. You can only have phase transitions in the infinite volume limit. You might think, well, sample of iron, 10 to the 23rd atoms. What really happens is you have something which is very sharp but not discontinuous. But in any case, from a mathematical physics point of view, we want to study the limit of infinite systems where you have a true phase transition. And so the kinds of things we do are we consider some sequence of graphs Gn that are getting bigger and bigger. For physicists, these would usually be, you take a regular lattice like the infinite square lattice, and then Gn's would be bigger and bigger boxes in the infinite square lattice. But mathematicians might like to consider other sequences of graphs Gn, like the complete graphs, or the complete bipartite graphs, or the cycles, or any reasonable sequence of graphs, and you may be able to prove the existence of a limit like this. Limit n goes to infinity, 1 over the size of the graph, log of this partition function, which for me is the multivariate Tutte polynomial, or maybe the univariate Tutte polynomial. This is the kind of limit that physicists are interested in. Roughly speaking, it says that the z's, well, we know the z's are exactly multiplicative if a graph is the disjoint union of two pieces, and this expresses that the z's are approximately multiplicative for certain large families. And so you look for limits like this, and maybe this will give you some function, f of q and v, and you ask, when can this function f fail to be analytic? And the answer is that log z can have singularities in the complex plane that come to pinch the real axis as n goes to infinity and create singularities in the limit. Now you ask, how can log z have a singularity? Z is a polynomial. There's only one way that log of an analytic function can have a singularity. It's the analytic function vanishes. So this, what I'm telling you now extremely briefly, goes back to Yang and Li in two papers in Physical Review in 1952, where they explained that one way of understanding physical phase transitions is to promote to a complex variable one or more of the physical parameters which physicists would normally consider to be real, like q or v. Look in the complex plane for zeros of the partition function, and ask where on the real axis can those zeros pinch in the infinite volume limit. Those are the possible points of phase transition. So complex zeros are very important for studying phase transitions. In particular, if you can find some region of the complex plane that is zero-free, uniformly in the size of the graph, then you can show that means that the part of that region that intersects the real axis is free of phase transitions. So one way of proving absence of phase transitions is to prove some theorem on zero-free complex domains for the partition function in either Q or V or both. And those are the kinds of theorems I'm going to talk about in the next 35 minutes. And I'd just like to quickly classify these theorems into two classes, soft or hard, which are interpreted in the mathematical sense, meaning of soft and hard. A soft theorem is one where the zero-free region is some very simple domain. Usually it will be either a half plane or the unit circle or something like that. And the theorem holds for large classes of graphs, for example, all graphs. Okay, so a soft theorem is one where you prove it by soft methods and you get a very general result valid for some huge class of graphs. A hard result, on the other hand, is one where the domain depends quantitatively on some parameter of the graph. For example, its maximum degree. Okay? And I will show in my talk some soft theorems and some hard theorems, and then you'll see in other people's talks some soft and some hard theorems. For example, Roberto Fernandez's talks will show how to prove some hard theorems. Okay, so let me start with soft theorems, and let me start with the spanning tree polynomial for graphs. So I said it was related to electrical circuit theory. Why don't I give you quickly the intuition? Here's my graph. I think of it as an electric circuit with resistances on each edge, and the VEs are actually the conductances, the reciprocals of the resistances on each edge. And then maybe I stick a battery between two terminals, and I want to compute all the currents in here. And of course, that's a linear algebra problem, right? You write down Ohm's law and current conservation and so on. You get linear algebra. In fact, what you get is the Laplacian matrix for the graph G with edge weights V applied to the vector of voltages or potentials at the different vertices equals the vector J of current inflows at each vertex. This is a kind of discrete Poisson equation. And the current inflows here might be inject 1 ampere in this vertex, pull 1 ampere out of this vertex, and 0 on all other vertices, and you want to solve for the voltages. And the first question in linear algebra, of course, is does a solution exist and is it unique? Well, it's obvious, actually, that if a solution exists, it won't be unique because you can add an arbitrary constant to all of the voltages on all of the nodes simultaneously, and that won't change anything because it's only voltage differences that have any physical meaning. Physically, that's because the matrix here is singular. All the row sums and column sums are 0, so it annihilates the vector 1, 1, 1, 1, 1. So you have to do something to get rid of that singularity. Physically, what you do is you declare one vertex to be ground. Doesn't matter which vertex. You put 0 voltage there. Mathematically, that means you choose one vertex, call it I0, the ground vertex, and delete row and column I0 from the matrix. I'll just write X I0. Delete that row and column. Then you can ask, is this thing singular or not? Well, the matrix tree theorem, this is this beautiful theorem. I don't know whether Kirchhoff proved it, but at least he wrote it down. Says that the determinant of the weighted Laplacian matrix deleting one row and column is independent of what row or column you delete, and it's nothing other than the spanning tree polynomial. So the solvability of electrical circuits is equivalent to the question of whether the spanning tree polynomial vanishes or not. So you see already how zeros are relevant. Now, let me give you two examples to show that electric circuits are not always solvable. Here, I'll take a battery, put two resistors in series with 1 ohm and -1 ohm. By the series law, 1 plus -1 is 0. They draw infinite current. Okay? Now you say, okay, come on. I mean, now I could get even mathematicians in the audience to say, come on, negative resistances are not physically realizable. Okay, fine. So I'll put I and -I, which physically, if you want, you can translate as an AC circuit at some fixed frequency. You have a perfectly lossless inductor in series with a perfectly lossless capacitor exactly at its resonant frequency, and again you draw infinite current. But then again you say, come on, perfectly lossless components are not physically realizable. Every inductor has a little bit of resistance in the wire. So that leads you to conjecture the following result. If all of the branches in this circuit are dissipative, that is, these conductances VE are complex numbers with strictly positive real part, and I should have said, and the graph is connected, otherwise there are no spanning trees and the circuit's not solvable. If the conductances have all strictly positive real part, then the spanning tree polynomial is non-vanishing. Now that's now a perfectly mathematical conjecture about the complex zeros of the multivariate spanning tree polynomial, and it's not just a conjecture, it's a theorem, which is fairly easy to prove by a two-line quadratic form argument, which basically formalizes the intuition about energy dissipation. And I don't know who this theorem is due to. I mean, you can find it hidden in a few electrical circuit theory books, and I have no idea who first proved it. But anyway, what this says, so this is a beautiful example of a soft zero-free region theorem for the spanning tree polynomial of an arbitrary graph. It says that the spanning tree polynomial of a graph is non-vanishing in the product of right half planes. And so it says in language that James Oxley and Dave Wagner and Young Bin Cho and I used in a recent paper, that the spanning tree polynomial has the half plane property, or sometimes called Hurwitz stable. And again, that's an amazing fact if you think about it. Consider the spanning tree polynomial for the complete graph on 10 vertices. Okay? So that is a homogeneous polynomial of degree 9 in 45 variables, n choose 2, with 100 million monomials, n to the n minus 2. Okay? I defy you, I mean, take a random polynomial of that kind. I don't know whether anybody has studied what is the probability that a randomly chosen polynomial has the half-plane property, but I bet it's very low.
Does it translate into eigenvalues of LG?
I'm not sure. I don't think so. I don't think so, but I'm not sure. Well, yeah, I mean, it certainly translates into, if you put in these particular complex V's, you shouldn't have any zero eigenvalues other than the trivial eigenvalue, zero eigenvalue. So yes, it does, it translates into the absence of a zero eigenvalue. But more than that, I can't say. It would be interesting to understand more about these properties. So the spanning tree polynomial has this deep combinatorial property, the half-plane property, and we can ask various things. We can generalize. So you see we've got this scheme of Q goes to zero limits, and we also have coming out of the blackboard the generalization to matroids. So you can ask for various generalizations. One is come out of the blackboard, generalize from spanning tree polynomials of graphs to basis generating polynomials of matroids, and ask which matroids have the half-plane property. That is, for which matroids is it true that their multivariate basis generating polynomial has the half-plane property. And that was the subject of the paper with James and Dave and Young Bin that I mentioned to you. And the answer is we have lots of sufficient conditions, we have lots of necessary conditions, and we don't know where the borderline falls between half-plane and non-half-plane property matroids. So that's a big open area to study. Another thing you can try to do is generalize back to connected spanning subgraph polynomial or spanning forest polynomial or both. And let me show you that. Let me pick the connected spanning subgraph polynomial because it contains, you see, v infinitesimal in the connected spanning subgraph polynomial is the spanning tree polynomial. So you can ask, might there be a zero-free region in the connected spanning subgraph polynomial, which when you do this, looking with a microscope to make v infinitesimal, it turns into a half-plane. So is the half-plane property a special case of something more general? And turns out the natural guess for the region in the complex v-plane, so well, in each VE separately, the natural guess is the disk of radius 1 centered at -1. I'll explain why that's the right variable in a second, but you see, in particular, if you focus on an infinitesimal neighborhood of the origin, then this blows up into the left half plane. And the left half plane is essentially equivalent to the right half plane because the spanning tree polynomial is homogeneous. So conjecture for all connected graphs, if you're in this disk, 1 plus VE strictly less than 1 for all E, then CG of V is not 0. Okay? So let me tell you a little bit of the history. The univariate version of this, where all the VEs are taken equal to a single number V, was conjectured in slightly different variables by Brown and Colborn in the early 1990s, based on some partial theorems and some numerical results. Then in, I think it was 98, Dave Wagner came up with an ingenious and incredibly difficult, but correct, I believe, well, I don't know whether it's correct because it was so difficult I was unable to read it, but it's probably correct because at least one referee probably read it. Proof of the univariate Brown-Colborn conjecture for series parallel graphs. Now, series parallel graphs are a tiny subset of planar graphs, which were a tiny subset of all graphs. But anyway, you do what you can. So that was 20 pages. Then, meditating on this and, again, thinking with this multivariate ideology, I realized you could generalize it to this multivariate Brown-Colborn conjecture. And then, instead, for the series parallel case, instead of proving it in 20 pages, you prove the stronger theorem in 3 lines. It sometimes happens that a stronger theorem is much easier to prove than the weaker theorem. In particular, the multivariate theorem is easier to prove than the univariate theorem because you have more flexibility. You can do induction on the number of variables with each variable taking different values. And let me give you the 3-line proof that for series parallel graphs, this multivariate Brown-Colborn conjecture holds. Well, it's true for K2, right? I mean, 1 plus V. No, I don't mean 1 plus V. I mean V. V is the connected spanning subgraph polynomial for a single edge, and that certainly doesn't have a 0 in this region. Now just do series in parallel reduction using the series in parallel laws that I erased on the other blackboard. So parallel, if you remember, was 1 plus V multiplies. So if 1 plus V, 1 plus V1 and 1 plus V2 are complex numbers of magnitude less than 1, then so is their product. So parallel reduction is trivial on this region. Series reduction specialized to Q equals 0, which is what we're doing here, turns out to be 1 plus V add, 1 over V adds. It turns out to be the same series law as for electrical circuits. Resistances in series add, and resistances are 1 over V. And you do, and so, but it turns out 1 plus V less than 1 is equivalent to real part of 1 over V is less than, I think it's less than a half, less than minus a half. Just a little geometry to do there. And so if you have two complex numbers with real part less than minus 1/2, there's some. What?
Not the minus sign. No absolute value on the real.
Say this again?
Absolute value shouldn't be less than a negative.
No absolute value, sorry. No absolute value. Just take out the absolute value. Sorry. Right, thank you. So that's a little fact about complex geometry. If you have two real numbers whose real part is less than minus a half, their sum has real part less than minus 1, and minus 1 is less than minus a half. So we trivially show that this domain is invariant under parallel reduction. You show with one line of algebra that this domain is invariant under series reduction. Therefore, the Brown-Colborne conjecture holds for all series parallel graphs. So that's the first triumph of multivariate ideology. Okay, here's the second triumph. After this theorem, I figured that the Brown-Colborne conjecture would be true for all graphs, and I worked hard to try to prove it and failed. Until one day, I get this email from this guy I had not previously met, named Gordon Royal, who said, "Did you know that the multivariate Brown-Colborne conjecture is false for K4? The simplest non-series parallel graph there is?" I said, "No." He had a computer example, and then we simplified the computer example to even have an analytic counterexample. And we worked harder. We actually proved that the multivariate Brown-Colborne property holds for a graph G if and only if the graph is series parallel. So the original theorem was as far as you go. But then, and here's the second triumph of the multivariate ideology, having in hand the multivariate counterexample for K4, we managed to turn it into a univariate counterexample for graphs that are built from K4 by expanding the edges to parallel edges. So I think, if I remember correctly, we took K4 and took these two edges on the side and expanded each one to 7 parallel edges and got a univariate counterexample to the univariate Brown-Colborne conjecture. And then if you don't like that, you might say, okay, but that's not a simple graph. Then we replace these edges by pairs of edges in series. And then I can't remember. I think we had, in the end, we had a graph, a simple planar graph with, I think, about 1,500 vertices and 3,000 edges, which was a counterexample to the univariate Brown-Colborne conjecture. But you wouldn't possibly have found that counterexample by any direct search or any other method, unless you're very smart, by any other method that I could imagine, other than starting with the K4 multivariate counterexample and then turning it into a univariate counterexample. So in an unexpected way, the multivariate ideology paid off for a second time in the study of these polynomials. So I'll just leave it there. There are huge numbers of open questions about the zero-free regions of these things. I should say, even though we showed that series parallel is the best you can do on the multivariate Brown-Colborne conjecture for graphs, it's still a partially open question for matroids. Which matroids have the multivariate Brown-Colborne conjecture? Okay, let me now, in the last 15 minutes, talk a little bit about hard theorems, and then you'll see more details in the talks of Roberto Fernandez and others. And so now let me concentrate on the chromatic polynomial, PG of Q, and I'm looking for zeros in the complex Q plane. You can ask more general questions, and I think Robert Schock and Norman Biggs and Jesper Jakobsen will all also show, I think, some zeros in the v-plane. But let me just concentrate on this to give you the flavor of some of the results. First of all, let me say that I think there are 4 different theories of zeros of the chromatic polynomial that you can look at and that we'll hear more about this week. One has to do with the integer zeros of the chromatic polynomial. Well, the integer zeros of a chromatic polynomial are just 0, 1, 2, 3, up to the chromatic number minus 1. So this is just the combinatorial theory of the chromatic number. And of course, there are many theorems bounding the chromatic number above and below in terms of other graph invariants. Second, the theory of real zeros, which Bill and others are going to tell us more about today and tomorrow. Third is what I and the other people I've mentioned are concentrating on, namely complex zeros. And finally, there's a 4th little theory that very little is known about, but we're going to hear a few examples of it this afternoon, what I call the algebraic theory. Namely, chromatic polynomials are monic polynomials with integer coefficients. So the roots are all algebraic integers. Algebraic numbers, but in fact algebraic integers. And you can ask which algebraic integers can occur as roots of chromatic polynomials. Or otherwise put, which polynomials with integer coefficients can occur as factors over the integers of a chromatic polynomial. That's a big, almost entirely open area with only a small number of theorems in it. But let me focus on this first 3. And let me just say, it's a natural thing to take a theorem at one level and ask if it extends to a higher level. Take a theorem, for example, about how the chromatic number is bounded in terms of maximum degree or degeneracy number or some other invariant, and ask, does it extend to real zeros or complex zeros? So let me give you an example of that. So this is how I first got into the subject. We take 2 theorems, which I think Bill will tell you about real zeros of chromatic polynomials. So the first theorem about real zeros that you get in this subject is that if Q is real and negative, then the chromatic polynomial is non-vanishing. It's very easy to show that the coefficients in the chromatic polynomial alternate in sign, so you can't have a negative real root. So let me use a colored chalk here to show where you cannot have roots there. So it's a natural question, is this the tip of the iceberg of some kind of Li-Yang type theorem? Is there a complex region that's zero-free that contains the negative real axis? And of course, a natural conjecture would be the left half plane. And indeed, around 1980, there was a person who was unfortunate enough to make that conjecture in print. Because if you calculate chromatic polynomials for small graphs and plot the zeros, they'll look something like that. But then Gordon Royle and Ron Reed came along and found by computer search a 16-vertex graph that had chromatic roots with real part, I don't know, minus 0.2 or something like that. So left half plane won't work, but maybe there's some region containing the negative real axis that is zero-free for all graphs. First question. Okay? Second fact that I guess Bill will also tell you, if G is planar and Q is greater than or equal to 5, then PG of Q is strictly positive. Of course, for integer Q greater than or equal to 5, this is the 5-color theorem. So this is a kind of real generalization of the 5-color theorem. It goes back to Birkhoff and Lewis in 1946, and there are now nicer, simpler proofs of generalizations of this by Douglas Woodall and Karsten Thomason in, I think, 1997. So 5 and up, there are no zeros for planar graphs. Of course, 4, there are no zeros. At least I think there are no zeros. That's the 4-color theorem. I think the proof is true, right? It's socially constructed as true. there are two independent proofs. So I assume they're right. I haven't studied them. And then a big open question, the Birkhoff-Lewis conjecture. Are there any zeros for planar graphs between 4 and 5? I don't think anyone has the slightest idea how to do this, because the proof of the original Birkhoff theorem for above 5 is, in a certain sense, analytic. The proof of the four-color theorem is totally combinatorial. We have no idea how to merge them. But it's a reasonable guess that the Birkhoff-Lewis conjecture is true. So then you can again ask, might there be a zero-free region containing the part of the real axis above 5 or even above 4? Again, you might conjecture real part greater than 4, but that doesn't work because there are pieces of the triangular lattice that have zeros with real part, I don't know, around 4.2. So that won't work, but you might get some region like that for planar graphs. And so you can imagine how exciting this was for me, a mere physicist, to conjecture a double generalization of the four-color theorem, right? To go from a point to a line to a complex domain. Now, granted, it might be that this theorem is easy and the boundary point is hard. That frequently happens. But that's not what happened in this case. Both of these conjectures, like most of my conjectures, are false. But what's interesting is that not just that they're false, it's that they're utterly, totally, radically false. They're as false can possibly be. Namely, well, I'm conjecturing that there's some zero-free domain somewhere. What's the opposite of that? The opposite is that the chromatic roots, well, there are a countable number of graphs, and they each have finitely many chromatic roots, so they can't touch every point in the complex plane, but they could be dense in the complex plane, and that's the title of my paper. Chromatic roots are dense in the whole complex plane. In fact, what you show is you study just these graphs, generalized theta graphs, theta SP. So you take p chains in parallel, and then each of those chains has s edges in series, and you consider just those graphs alone, and as you vary S and P, the roots become dense in at least the whole complex plane, with the exception of the disk of radius 1 centered at 1. With the exception of inside that disk where I don't know what happens, outside that disk, the roots go densely everywhere as S and P go to infinity. And again, you would never in your life discover this numerically, but you discover it fairly easily by playing with the series and parallel laws. So, and asking what domain, how do things map in the complex plane with the series and parallel laws? So, okay, that shows, by the way, that there's a big difference between the theory of real zeros and the theory of complex zeros. A hypothesis that succeeds in bounding the real zeros does not bound anything about the complex zeros. The complex zeros go densely virtually everywhere. So a hypothesis that works at one level may not work at the next level. These theories are quite different. Nevertheless, it is a reasonable thing to try, and let me show you a second version of this type of argument that works, which is take a hypothesis that bounds the integer zeros. Well, the first thing that you prove is in the theory of chromatic numbers that the chromatic number is at most the maximum degree plus 1. You can always color a graph with maximum degree plus 1 colors. You just use the greedy algorithm. You just start coloring using some color that's not used on any of your neighbors. And so this says that PG of Q has no integer zeros greater than delta, where delta is the maximum degree. Because the integer zeros are all the numbers up to chromatic number minus 1. Okay? So there are no integer zeros greater than delta. So that leads to the following conjecture. PG of Q has no real zeros greater than delta. And this is a big open problem, which, will you talk about this? in your talk? No. Okay. But it's a big open problem. But again, it might be that after somebody proves it, we'll see that the proof is easy. Or it may be that it's false, in which case the counterexample would probably also be easy. Or maybe it's true and the proof is hard. We really have no idea. But I think this is a reasonable conjecture, that there are no real zeros greater than delta. About complex zeros, what is known is there are no complex zeros with magnitude of q greater than, well, my first bound was 7.963907 delta, and now Roberto and Aldo have reduced this to how much? 6 point something? 6 point something delta, and Roberto will talk about that on Wednesday. So again, we don't know what the sharp number is. This is interesting because the proof is based on methods from mathematical statistical mechanics. And Roberto is going to give you an introduction to those on Wednesday because we think that these methods, which are rather unusual for graph theorists, could be very useful and powerful in studying some of these types of problems. And we really don't know what the optimal constant here is. Might be 2, might be 1.5. Can't be bigger than 1.5 because it turns out that the complete graphs K and N have complex roots that go out to, I think it's around 1.5 times delta. But, and let me stop by saying one thing. This idea of bounding chromatic roots in terms of maximum degree is unnatural. Let me give you an example. Consider a tree, right? You can have maximum degree extremely high in a tree, but nevertheless, the chromatic polynomial for any tree of n vertices is q times q minus 1 to the n minus 1. The chromatic roots are 0 and 1. So maximum degree is somehow unnatural for bounding chromatic polynomials. Another way of saying that is chromatic polynomials, and more generally the multivariate Tutte polynomial, factorize not only over disjoint unions, which virtually any graph polynomial will, but it also factorizes over unions at a cut vertex up to a factor of q. And another way of saying that is the right way of looking at the multivariate Tutte polynomial is matroidal. Matroids can't see the difference between a disjoint union and a cut vertex, and neither can the multivariate Tutte polynomial. And maximum degree is definitely not a matroidal concept because it refers to vertices which don't exist in matroids. And so the goal is to try to find a better invariant, one that respects this decomposition into blocks for bounding the real or complex zeros of the multivariate Tutte polynomial. And let me just give you our conjecture for what this invariant is, even though we have no proof to support it. It's what Bill Jackson and I call max-max flow, which means take two vertices and look at the maximum flow between them. That is the maximum number of edge disjoint paths between them. And then take the maximum over all pairs of vertices. So it's like edge connectivity, but in edge connectivity you would take the minimum over pairs of vertices. Here you take the maximum. And then we believe, and by the way, it's easy to show that max-max flow is bounded above by delta 2, the second largest degree. And I should say, by the way, that these theorems on maximum degree extend to second largest degree. You're allowed one vertex of very large degree, and that won't kill the fact that the chromatic roots are bounded. Two vertices of large degree, and all hell breaks loose. That's what you see there. So max-max flow generalizes the second largest degree theorem, and Bill Jackson and I think that there should be a theorem, complex zeros are bounded by some multiple of the max-max flow. But we have no proof. Okay, so I'll stop there. Oh, exactly on time. And take questions, if there are any.
If you look at the chromatic polynomial and the roots of chromatic polynomial,
And probably there's another way to look at the zeros, the multiplicity of the zeros. And for instance, for the integer zero roots, okay. And you look at the zero, okay, it's always, q equal to 0 is always the root over there.
Right.
And you look at its power, that counts the number of kinetic components.
Right. That's right. The multiplicity at q equals 0 counts connected components.
Yeah, if it's
the
connected,
multiplicity at q
one.
equals 1
Yeah.
counts blocks. And I don't know, does anybody know what the multiplicity at q equals 2 counts?
The 2 is unknown.
Yeah, so that's an open question already at q equals 2.
Yeah, another example.
What?
Yeah, another example for three kinetic graph, the root to the multiplicity can be bigger than 1.
Okay, so it's an interesting open question already to understand the multiplicity of q equals 2. That's right. So I haven't said anything about multiplicities, but that is, you're absolutely right. That is another angle. If you want, it's complementary to the kinds of things that I think Harry's going to be talking about this afternoon, which has to do with which factors can you get when you factor over the integers. The other question is what multiplicities are possible for these different factors. So you can see there's a huge area of open problems. Yeah. Yeah.
Those sort of conjectures you made to a degree, have you thought about making similar conjectures where the parameter is tree width?
Where the parameter is
Tree width?
tree width.
Trees are tree width 1 and series parallel networks are tree width.
Yeah, well, let me think for a second. Series parallel networks, you can see the series parallel by itself doesn't constrain the complex zeros, but it does constrain the real zeros. The real zeros for a series parallel graph are all in the interval 0 to 2. I think it's known. I could be wrong. I think it's, so series parallel graphs are tree width 2?
Yeah.
So I think it's known, I could be wrong, I think it's known the tree width k, all the real roots are in the interval 0 to k. But I'm not totally sure whether that's known. If it's not known, it's a conjecture that I'm putting out right now. Because it is a reasonable, right? I mean, you understand tree width 1 and tree width 2, and you understand the theorem about series parallel graphs, you're right. That is a natural conjecture.
Doesn't that sort of hinge on the simple formula that if you take two graphs and you stick them together over a complete graph with R vertices, shall we say, then there's a simple formula for the stuck together.
I'm sorry, does which thing depend on
Well,
that?
this business about tree width and the multiple integer zeros, because the formula is you take the product of the chromatic polynomials and divide by the chromatic polynomial of the complete graph, which is just z times z minus 1, q,
Right.
q times q minus 1, and so forth. So you get the integer zeros factored out.
Yeah, it's certainly true that
I'm not saying it's the full answer, but I think that's sort of that leads you on to these multiplicities and the tree width.
yeah, it's definitely related to the multiplicities. If you glue two graphs together that overlap in a clique, then their chromatic polynomials factorize up to a simple factor, which is the chromatic polynomial of the complete graph. And therefore, if you want to consider these multiplicities, you have to first define some notion of a graph being prime relative to these clique unions. Otherwise, things would be trivial.
So you said that you don't know if the chromatic polynomial of a planar graph has any real zeros strictly between 4 and 5.
Right.
Do you know if it can have zeros strictly between 3 and 4?
Gordon Royal answered that question a few years ago in what I think is an incredibly beautiful paper, because it solved a long-standing problem, and the paper is so easy that, I mean, not so easy, but it's so nice and simple that you could assign it to an advanced undergraduate class, I think is fair to say. It uses some elementary graph theory and some elementary linear algebra, and Gordon explicitly constructed a family of graphs, of planar graphs, in fact, plane triangulations, whose chromatic roots approach 4 from below. I guess it's still not known where in the interval 3, 4, I mean, it's a reasonable conjecture that maybe the whole interval 3, 4 is attainable for chromatic roots of planar graphs, but I don't think anyone knows. Yeah, Bill.
So I always ask you this question, Alan. So For the Brown-Colburn conjecture, it's conceivable that it might be true for three connected simple graphs.
Brown-Colburn. I thought you asked me three connected simple graphs for this question of the other question of do the roots go everywhere. So I haven't thought about Brown-Colburn for restricted families of graphs. So by the way, of course, that is a natural thing to do, right? Any of these theorems could be any graph hypothesis or conjunction of graph hypotheses implies something on zero-free regions or conversely on existence of zeros in regions. There are infinitely many possible theorems of that type. Some ridiculously small fraction of them are true, and your job is to find them. We know very little, so I don't know whether that hypothesis will save the Brown-Colburn conjecture. But it is a natural question I should have said here with these series parallel graphs. But to get these roots to go everywhere, I used these generalized theta graphs and used the series parallel laws over and over and over again. So you might ask, what if I consider three connected planar graphs? Can their chromatic roots go everywhere? And I think that the answer is also probably yes, but Jesus and I have only numerical evidence for that, not a proof yet. Yeah, Roberto.
Anything of these has been adapted to random graphs?
I don't know. I mean, I don't even know exactly what the question. I mean, you don't. I mean, I guess the question would have to be: consider the roots of G, and then prove probabilistic theorems about where those roots do or don't go for some probability distribution over G, like GNP. I think you've just invented a new area that will keep people busy for a few decades.
I've got a question.
Yeah.
Oh, you said that, I'm not sure if I'm listening wrong. Okay, that means you said that the set of complex roots of all graphs, of chromatic polynomials, all graphs is dense in the complex plane.
Right. I'm sorry. So let me explain that a little bit better. For series parallel graphs, you see from the generalized theta graphs alone that it's dense in the whole complex plane except for that little disk. That's what I proved, okay? An immediate corollary of that, which I didn't immediately see, but Jason Brown did, is that if you take all graphs, you get the whole complex plane, because you take these guys, and you take these guys join K2. So take an edge out here, and connect these two vertices to all of the vertices there. The chromatic polynomial of join K2 is Q minus 1 times PG of Q minus 2, because you have one way of coloring one vertex of this edge, Q ways, Q minus 1 ways of coloring the other vertex, and then everything else has to be colored with Q minus 2 colors. So if these guys have roots that go densely everywhere except for this disk, joined with K2 will shift the disk by 2, and the union of those two things will cover the whole complex plane. So if you take generalized theta graphs and generalized theta graphs join K2, that set of graphs has roots that are dense in the whole complex plane. But, as Bill pointed out to me, for three connected planar graphs, it's an open question where the roots can go. Okay, thank you.